We're going to have a wonderful evening this evening. The wonderful lecture on decibels and what decibels are and what decibels do and why we use decibels and why don't we use volts and amps. There's reasons for everything in this hobby. So yeah, decibel. Let me just get, let's get to the right screen. Decibel, something to remember, is a logarithmic unit used to measure or represent a ratio of two values. Now, if we look at a ruler or distance in the metric system, it is linear. In other words, 1 to 2, 2 to 3, 3 to 4 is always the same distance or the same amount of movement. In decibels, this movement is logarithmic. So it's not 1 to 2, 2 to 3. It becomes 1 to 2, 2 to 4, 4 to 8 as an example. That's logarithmic. The decibel unit value is always derived from the comparison between a reference and a baseline and a real-time measurement. So, and you'll see tonight when we go through all these things, in decibels, I've always got to compare one value with another value. So I've got a baseline, or I've got a reference, or I've got a starting point, and I've got an end point. And I compare the starting point with the end point. I compare the reference to the measured value. I compare the baseline to the measured value. And that ratio then becomes decibel. One way to explain it was probably the easiest. I got hold of this little drawing for you. So if you look at this, in sound, they say 0 dBs is our reference. And this is when it is quiet. There is nothing. Obviously, in real life, I don't think even in space you get 0 dBs because there's cosmic noise. But 0 dBs is supposed to be completely silent. Then somebody that breathes, for example, they say is 10 dBs of increase over dead silence. So if we go say dead silence is 0, somebody breathing is 10 dBs. People talking to each other, they say is 30 dBs because they're comparing dead silence with the people talking. And if we move it to natural life for us, or explanatory life, if I move from 0 dBs to 10 dBs in sound, listen, we're comparing sound now, that is twice as loud. So 10 dBs is twice as loud as dead silence. Somebody breathing is twice as loud as dead silence. If we look at these people talking at 30 dBs, that is 8 times as loud as complete silence. And where do we get that from in sound? That jump is 2. That's another jump of 2, another jump of 2. So 2 times 2 times 2 becomes 8. But this is now in sound because of our baseline. If we bring it to our hobby, amateur radio, this is what we obviously want to learn about. I've got two formulas, and these are the two magic formulas you need to know for the exam. And if you understand these formulas, you can pass the exam, the chapter on decibels without a problem. If I compare power with each other, so in other words, the output power of my transmitter compared to the input power of the transmitter, I get the logarithmic value of that ratio and I times it by 10. And that gives me a dB value in terms of power. If I work with voltage or I work with current, I compare the output voltage with the input voltage, the logarithmic value of that ratio times 20. Now, how do I remember times 10 and times 20? It's easy. Go to your triangle on Ohm's law. Voltage, current, and resistance are singular values. In other words, you cannot go deeper than voltage, current, and resistance. R, V, and I, that little triangle you did when you did Ohm's law, keep that in your mind. Voltage, current, resistance is singular values. I can't break them down further. So I always have to use 20 times the log of that ratio. Power is not a singular value. What's the formula for power? If we go back to our textbooks, power is the voltage times the current. There's two things I have to multiply with each other to get power. So I use only 10 log that ratio. So that's an easy way to try and remember it. If you see voltage current in your exam paper to work out the decibel value for a voltage ratio or a current ratio, just think of your triangular Ohm's law. You can't break voltage, current, and resistance down further. But power is two values multiplied to each other. So I hope that helps you to remember when to use 10 log and when to use 20 log. In amateur radio, where do we use these horrible things they call a decibel? Okay, we use it when we look at the gain of the antennas. We use it to look at what's the loss of my feed line. What's the loss of connectors that I use in my hobby? What is my total radio network at home that I'm going to set up when I get my license? What's the total gains or the total losses of that radio network? Okay. The one thing with decibels to remember, you always have to have the same units of measure for the ratio that you're calculating. So in other words, let's take an example. If I want to calculate power, let me just go back here. So if I want to calculate power, I've got to use, for example, peak power out, peak power in at 50 ohms. I can't now take an RMS power and compare it to a peak power. I've got to use the same units of measure. The same when I work with voltage and current. I can't use voltage RMS here and I use voltage peak to peak here. So both the voltages have got to be of the same unit of measure. So they've either both got to be RMS or they've both got to be peak or peak to peak or whatever the unit is that you've measured in. And in power-wise, it's got to be referenced to a constant input impedance and an output impedance. So I can't have a 600 ohm input impedance and a 50 ohm output impedance, because then the ratio of the power out and the power in is not strictly theoretically the same thing. I'm not comparing apples with apples. I'm comparing apples with pears. Okay, so they may ask you, and I've seen it in some of the previous sample papers, what is the requirement for the ratio? And the answer is going to be the impedance. Let's go back here where I was, sorry. The assumption is that the input and output impedance or measurement units are the same. So remember that. Okay. Just out of interest, it is in your book as well. There was a nice dude that lived more than 100 years ago, Alexander Graham Bell. He was the guy that devised this method of measuring stuff. The only thing that changed after he developed the bell was the metric system added the deci in front, because the jumps between one bell to two bell was too big. And that's where it became decibel. Deci in the metric system is times 10 or divide by 10, depending on how you look at it. Okay. Now we're going to have some fun. I'm going to explain to you what we want to do, and then I'm going to give you a couple of minutes to think about it. And if you've got a piece of pen and paper there, hopefully you can put a couple of things on paper for you to consider. I have the following HF radio, which is neatly placed 50 meters away from my half-wave dipole antenna dangling in the garden. My HF radio's transmitter is producing 100 watts of power into 50 ohms. My UHF connector has 0.5 dBs of insertion loss. My RG58 coaxial cable has got a 20 dBs per 100 meters attenuation. And my antenna's got a SWR of 2. So the question to consider is how much power are being radiated from the antenna. Something to mull about.
How long is your RG58 coax cable?
Assume 50 meters. He's saying it's 50 meters away from the. I'm using that, yeah.
Okay, hopefully everybody's done their bit. Why am I doing this exercise with you? One, you're going to get something similar most probably to answer in the exam. And two, no, Peter, you're wrong. Yes, you're wrong. Okay, you're going to get something like this in the exam, but also what happens is you get hams and you get radio amateurs. Now, I'm not a great fan of hams, unfortunately, but I'm a great fan of radio amateurs. Radio amateurs are guys that do their hobby technically. And there's going to be outoppies at the flea market that's going to tell you just gooi a piece of wire over a tree. And there's some 5-year-old cheap coax which they want to sell for R2 a meter. If you take the insulation off the coax, it's green already from all the corrosion and the moisture penetration, and things like that. There's a reason why in our hobby things are slightly more expensive if you want to do it properly. So let's look at, come on. Okay, let's look at this example. My radio is 50 meters away and I'm using a half-wave dipole antenna. So what happens? My transmitter is producing 100 watts into 50 ohms. If I do the calculation, that equates to 50 dBm. Okay, 100 watts is 50 dBm. I've bought really cheap Chinese UHF connectors at the flea market for 15 Rand a piece. They start melting when I take my soldering iron out the drawer. So they've got a loss of half a dB per connector, and I've got 4 connectors, one on the radio, one on the coax beginning, one on the coax end, and one at my antenna. So I'm losing 2 dBs of power because I'm using cheap Chinese insulation UHF connectors. Then I somebody told me, no, man, you saw me use RG58. It's cheap coax. Wonderful stuff. You can buy it cheap. Not on 50 meters of distance away from your radio. Definitely not. But we're using it. So we're losing 20 dBs per 100 meters. That gives me minus 10 dBs of loss in my cable alone. Then I go, and because I didn't bother to trim my antenna's SWR, I just hoid it over the tree like the Otopie said. I've got a SWR of 2, which gives me a power loss of 10%. Okay. Now we start calculating. 50 dBms minus 2 dB loss of the connectors, minus 10 dBs of loss because of my cheap coax. But here's a good thing. I'm using a half-wave dipole antenna, and that's got a gain of 2.15 dBs above my reference being an isotropic antenna. So at least there I'm gaining 2 dBs. Just out of interest, the difference between an isotropic antenna, which is used as a reference point, it radiates energy in all directions. So in other words, the radiation pattern of an isotropic antenna looks like a soccer ball, where a half-wave dipole antenna, it looks like a Krispy Kreme ring donut. So if I look at the axis of my antenna, in perpendicular with the axis of my wire, of my antenna wire, I've got a radiation pattern looking like a Krispy Kreme donut. So it's radiating more power perpendicular to the wire than what it is radiating along the wire. So that's why it's got a gain of 2.15 dBs over an isotropic antenna. Okay, so if I do the calculation, I get roughly 40 dBms, which equates to 10 watts of RF power. Now I go further. I'm losing 10% because my SWR is not too great. I didn't bother trimming my antenna. So my final radiated power is only 9 watts, 39 dBm. So I spent 25,000 Rand on an HF radio, and I couldn't spend 1,000 Rand on the balance of my system. There's a sort of a rule of thumb I always say to the new people. Whatever you spend on the radio, you must be prepared to spend on the balance of the system. So in other words, connectors, cables, antennas, everything that goes with the radio. Otherwise, you are, in some sense, wasting money. If you look at this example, 100 watts becomes 9 watts. Is there questions on this one before I move on to the next scenario? See, Peter is typing madly there.
Johan, ek wil miskien net by sê dat die RG58 se los is gekoppel aan die frekwensie waarop jy dit gebruik.
Ja.
So met HF kan jy op 'n kort afstand nog daarmee wegkom. 'n Korter afstand op VHF, maar op UHF kan jy dit glad nie gebruik nie.
Ja. Yeah, for example, just out of interest, the UHF connector's limit is 200 megahertz. Above 200 megahertz, you can't use a UHF connector. But let's look at the next scenario. I've now done my homework properly, and I didn't listen to the Otopies. I did some studying, and I looked at the topic properly. I've still got my transmitter, which I paid 25,000 Rand, nice shiny out the box for. It produces 50 dBms. But now I've gone to Web Industries and I bought some Telegardner UHF connectors at 150 Rand a piece. They are about 10 times the price of the cheapie, but that's what you get, what you pay for. But they've got an insertion loss of 0.05 dBs. And it's true. These figures aren't sucked out of my thumb. It comes out of the books, the data books, data sheets. So the Telegardner one has got a 0.05 dB insertion loss, so my total loss is only 0.2 2 dBs. What was my loss for the cheapies? 2 dBs. Okay, so I've already got a factor 10 improvement. Then I've decided to invest in LMR 400 coax cable. If we buy it new, it's about 40 Rand, 43 Rand a meter. So for 50 meters, you can calculate what you need, but it's only got a loss on HF of 2.2 dBs per 100 meters. That's minus 1.1 dBs for my 50 meter length of LMR 400 cable. I did my homework and I trimmed my antenna, so I lengthened or I shortened my antenna until it resonates the best it possibly can on the frequency I want to use it. So I've been able to bring down my SWR, and when you do antennas, you will get a nice lecture on standing wave ratios. I've brought down my SWR to 1.2 instead of 2. Which means I'm only losing 0.8% of what I put onto the antenna. So now I start the calculations again. 50 minus 0.2 minus 1.1. My antenna's got a gain of 2.15. And that gives me 50.85 dBms, which is 121 watt. Now the first thing you're going to ask me is, how can you get that? Remember, we said a half-wave dipole. It's got a radiation pattern looking like a Krispy Kreme donut. So in other words, in the perpendicular direction of the antenna, I'm putting 121 watts of energy into the air. That's what it means. Okay, I lose the SWR part and I end up with 120 watts of effective radiated power on my antenna. You'll see somewhere in your manuals they talk about ERP, effective radiated power. So that's what my antenna is producing for me in this scenario. So yes, I've spent a lot more money, but not close to 25,000, but just by changing to decent connectors, decent cable, and doing my work properly and trimming my antenna's length to resonate correctly on the frequency I want to work, I've been able to go from 9 watts to 120 watts. And you'll see everything we've done in dBs. That's why dBs is so nice. Okay, any questions?
Ja, net 'n vinnige vraag. Jou eerste berekening was dB en hierdie is dBm. Is daar verskil tussen dB en dBm?
Ja, ek sal nou vir julle wys wat's die verskille. Okay, any other questions? Ander vraag? Okay, let's go to this one. This is what I've been asked now. Okay. When we look at dBs, you'll see these funny things appearing behind the dB symbol. When we talk about dBs without anything behind it, okay, there is no reference point. There's no baseline. I'm purely comparing two values. Doesn't matter if it was a start or an end value or a midway and endway value. I'm comparing two values without a reference. That gives me straightforward just dBs. If I now reference my calculation for dBs to 1 milliwatt of RF power, I use the term dBm. So in other words, if I say, let me just go back here. So if I say my transmitter produces 100 watts and I say it's 50 dBms, it's because if you do the calculation, 100 divided by 0.001 times the log times 10 will give you 50 dBm. Because what do I have to compare the 100 watts with? I've got nothing to compare 100 watts with. So then I use the term dBm, which is here. So if I do the ratio calculation, it's 100 watts on top of the line. It's 0.001 watt below the line. The logarithmic value times 10 will give me dBms. I also get, sometimes you'll see it in places that they talk about dBW. All it means that it's referenced to 1 watt. So in other words, If I put 100 divided by 1 and I do the log times 10, the value that I get there will be a dBW value. But the more common one you'll find in the hobby as you progress with your amateur career is dBMs. dBW is used not that often. Then this one, dBc, is used when we characterize the response of filters and oscillators. When we look at things like jitter and drift and things, we would do the calculation using a dBc comparison. If we move to voltages, we get a thing called dBV, which is reference to 1 volt RMS. So if I've measured a peak value of voltage and I need to do the calculation here, I actually need to convert that measurement that I had, say it was 1 volt peak, I need to times that by 707 to get the RMS value, and then I can put 1 divided by the RMS value of what I measured. I can't put 1 volt RMS on top and 1 volt peak to peak or 1 volt peak at the bottom. I've got to use the RMS value. dBu is reference to 0.775 volt. You won't see this a lot. This is used in the telephone, or used to be when there was the days before voice over IP telephones, the good old analog phones we had in our homes. They used the dBu version of it, or the dBu measurement. They said, okay, your telephone, the signal coming from the exchange needed to be so many dBus, otherwise it was a bad line. Another one which have kept that's crept in over the last, I don't know how many years, is called dBFS, which you'll also see. This we use in the modern world with all these software-defined radios, which we will do in a chapter later in September. But that's where dBFS comes from, if you see it. Now, here's the interesting one. dBi is my antenna gain to a isotropic antenna. But in a lot of cases, it's more a mathematical value than anything that's really realistic. One you will find a lot in paperwork is they use the term dBd. So in other words, a half-wave dipole is termed as 0 dBd. So if my antenna's got a 3 dBd gain, it means that it's got 3 dBs better performance than a half-wave dipole. But that also then means if I wanted to put it into dBi terms, it would be 5.15 dBi of gain. I hope it makes sense. And then the last one I've got here for you is dBSPL. That's used to reference to acoustic power, 20 micropascals of acoustic power. And where do we use this? If we start buying fancy studio microphones or fancy microphones for our radios one day, it's important to look at the dBSPL value of the microphone that I'm buying for my radio. And that was dBs, people. Questions? We have total silence. Okay.
Alles verloren.
It can't be alles verloren, man.
Nee, that logs
Ek probeer dit so maklik as moontlik maak.
I think I'm gonna parrot fashion everything else, and yeah, I'll get 0 for this one. I don't know this. I need to spend time with this. I hope it's only like 1% in the exam.
Yeah, it's a short chapter and it's not difficult. It's I suggest read your manual as well, and come back if you've got questions.
Yeah, no, I'll definitely do that.
Okay.
Just another question. Sorry, might be not related to this chapter. They also refer, I think, in terms of power, PEP, or am I incorrect?
Yeah, peak envelope power.
Envelope, is that what it's? Okay.
Yes, peak envelope
So
power.
will we still get to something about that in
Yes,
the main?
when you, yeah, it is, I think it's under the transmitters chapter, if I remember correctly. Yeah, either there or the digital modulation one. I know it's somewhere in one of the chapters.
All right.
Yeah, that's
100%.
PEP, peak envelope power.
Yeah. Okay, good stuff. Thanks.
Okay. Let's have a quick look at the questions. Let's see who can spot this one right. Question
I gotta
one.
admit, sorry, Johan, I
Yes,
gotta
Cliff?
admit, I didn't answer nothing here really, so you're not gonna get a beep out of me. Just being honest here.
An increase in power from, let me try and make this a little bit bigger. Yeah. An increase in power from 250 milliwatts to 1.25 watts is equal to a gain of. Okay, first thing now, which formula do we use? 10 log or 20 log?
10.
10 log, because it's power. It's not voltage or current, it's power. So we're going to use the 10 log formula. Remember now, the units of measure is going to be the same on top of the line and bottom of the line. So I've either have to convert the 1.25 watts into milliwatts, or I've got to convert the milliwatts into watts. They've both got to be watts, or both got to be milliwatts. So you can do it either way, it doesn't matter, your answer will be the same. But they've put this one as a trick for you to remember you can't work with milliwatts and watts on the same formula. This one's got to change, or that one's got to change. Okay, so what does it spit out for you?
7.
7 dBs, B, correct. Okay, then a transmitter with a power output of 100 watts is connected to an antenna with 11 dBs of gain. I tell you, this is a moose nice antenna if it's got 11 dBs of gain, but never mind. By means of a coax cable with a loss of 1 dB, and this is also a very good coax cable, the effective radiated power of the transmitter coax antenna combined is, again, we're working with watts, so we've got to convert 100 watts to dBs. And from our example, you should remember what 100 watts changes to in dBs. How do we get to the 50 dBs? Remember, we said we're working with 1 milliwatt reference. So 100 divided by 0.001, 10 times the log of that will give you 50 dBm. Any guesses on the answer?
If I take a wild guess, I'll say C with that 11 dB gain.
Any more guesses? John, you had a guess? Yeah, it is C. It's 1 kilowatt. Correct. Okay, 3. A 20 dB attenuator is placed in line with a 40 volt RMS signal. Assuming the impedances are all remain constant, what will the reduced signal be? So in other words, on the other side of the 20 dB attenuator, how many volts RMS will I get out? So now I've got to take which formula? 10 dB, 10 log or 20 log?
Volts, isn't it? 10
Yes,
log.
20 log. It's volts,
20.
it's not power. So we got to use the 20 log formula, and we just work it the other way around, where we've got the dB value and we've got the top value. We need the bottom value of the ratio. So if we do our mathematics, we should get an answer of
4.
4. It's D. Okay, 3D. 4. The power gain of 4 is equal to
6 decibel.
6 decibels. Wonderful. You can go write the exam. It's not that difficult. A signal with a power of 1 milliwatt is applied to the input of an amplifier that has a gain of 13 dBs. The power of the output signal will be
20 milliwatt.
C, 20 milliwatts. That is correct. And that's the questions. Again, they are at the end of the presentation, so I'll just flip that up so that it records. So if you want to go back to the questions and the answers, they will be at the end of the presentation. And that was decibel notation, people. Actually quite straightforward and easy. We're seeing each other next week again for filters, which is also a nice lecture. Filters going to be a bit longer. There's quite a bit of stuff we have to go through with filters. So yes, Henry, I am done for the evening with the lecture.
I'll say, thank you, Johan. I'm going to stop the recording. And yeah.